What's up, guys? I'm making some videos here at home because this could be the week that baby Chandler comes, and I won't be in class if baby comes to be able to teach you this. I wanted to make sure that you got a good jump on the new unit we're going into. We're going into radical functions, and I want to just go over some things that you probably actually already know and have been exposed to, but we've not done a lot of it this year. So what I want to do today is this actually follows along in your notes for the note packet. It's the first one is parts of the radical, number of roots, and things like that. So I want to run through this stuff with you and just make sure you get a good foundation. So hopefully this won't be too lengthy, but I do want to make sure I get some good, give some good tips here. So let me turn this thing around. Yes, you can see my mess on the table there. All right, so let's jump in. All right, so some things to know. Perfect squares. Remember, perfect squares is like 4, 9, 16, 25, da 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 da. You remember, like 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25. I would recommend knowing at least all the way up through 15 times 15, which would be 225. Me personally, I would at least go through 15. Just know those. Those are handy numbers to have. Your perfect cubes. Now, with perfect cubes, you're thinking, okay, a number multiplied by itself 3 times, right? So like 2 cubed is 8. 3 cubed is 27. 4 cubed, 16. About 64. Da 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 on to infinity. Wait. I think I made a mistake. 16. Yeah. No, I'm right. All right. So you want to have a good working knowledge of these right here, because these right here are going to be your best friend. You might even want to know your perfect fourths. Oh goodness, I'm just throwing everything around here, aren't I? It'd be a good idea to know the first few of your perfect fourths, because you may be asked that every once in a while. So make sure you're familiar with these. All right, so let's move on to like just parts of the radical expression here. This right here is called your index number. This underneath the radical is called your radicand. And of course, this thing is obviously your radical sign. Okay, so your index number, to help, and I'm gonna explain this more in a minute, but this right here is like if you have the square root of square root of 11. There's an understood 2 there. So we've talked about that before, but make sure you remember that number right there is like basically saying, okay, whatever number's under here, this number was derived by saying some number multiplied by however many times this number is. Now I'm going to explain that more in depth here in a minute, but let's just cover a couple more things here. So number of roots. Let's do a couple of them here. So we got square root of 16. That's an easy one. Square root of 16 is 4, but you have 2 roots. You have plus 4 or minus 4. So if you think about it, if you take positive 4 and you square it, 16. If you take negative 4 and you square it, it's also 16. So take note of this. Your underneath here is a positive number, and you have an even index number. So pay attention to this. Let's look at square root of 289. So 289, just happen to know that's a perfect square. That's 17. So a plus and minus 17. You need to make sure that you list those. Let's take a look. So let's take a look at what if you had square root of a -4? Well, what number can I multiply by itself and get -4? Well, if we go back and think about our polynomials and all that, remember we discussed how this is not a real number. It can't have a negative under the square root, right? So this right here has a complex. Oh, sorry about that, guys. Let me fix that. Hang on, let me see if I can lock this in. Okay. That has a complex solution. And if you remember, that was like plus and minus 2i, right? So just bring that back into your remembrance. Now, if you have like let's do an easy one, the cube root of 8. Cube root of 8, remember, you're saying what number multiplied by itself 3 times gets me 8? Well, that's 2. Now, this is not a plus and minus 2. This is just simply 2. Here's why. 2 times 2 times 2 gives me 8, right? There's 3 2's. 3 2's. The reason I cannot put a negative with this 2 is for this reason. If I said -2 times -2 times -2, that gives me a -8. Not what I started with. So, that doesn't work. So, some things that you, in your mind, you should be kind of we're about to fill this chart in here, but I at least want you to start just thinking about this. So, you have an odd index number. You have a positive radicand. You're only going to have a positive root, one positive root here. Now, it is possible when you have an odd index number, it is possible to have a negative root. This can be done. I'll use another easy one to kind of set the tone here. So let's say I say the cube root of -125. So -125. I know 125 is 5 times 5 times 5. Now, if I do -5 times -5 times -5, that gives me a -125, which is exactly what's under here. But and the reason that it's got to be a negative and not a positive is for this reason. If I took 5 times 5 times 5, that gives me 125. Not what I started with, right? So here's some takeaways. If I have an index number that's even, and it's got a positive radicand, it's a real root, so it's not an imaginary. And the number of roots, I have 2 of them, and they are, it's going to be a plus and a minus, kind of like right up here. If I have an odd index number and it's positive, so like this one right here, this scenario, I have a real root, but I only have one of them, and it's going to be a positive root. If I have an odd index, down here, if I have an odd index and I have a negative radicand, that's going to give me a real root. Even though it's negative, it's real. It's going to be one real root, and it's going to be a negative root. Here's one that has a star next to it. So what if I have, what if I've got an even index number? Let me get up here. So an even index number, but the radicand's negative. What happens? You've got a complex solution, or an imaginary. An imaginary solution. And it's going to be 2 of them. It's going to be a plus and minus. They're just going to be imaginary numbers. It's going to have that that I in it. So let's jump down here to 7. Let's just dive right into solving some of these. So if I'm solving the square root of 117, here's I'll show you 2 ways. I'll show you 2 ways that you can go about this. You can go But my preferred way is this. First, I look at it, see, okay, is it a perfect square? Oh, I'm sorry. Is it a square root, a cube root, fourth root, whatever? So if it's a square root, if it's a square root, I'm going to go back and I'm going to start thinking of all of my perfect squares. Okay, so I'm thinking those. It may be to your benefit to list them down here on the side where you can just have them there close proximity. But here's what I do. I take this number and I say, okay, let's take this number. Let's find the biggest one in my list. So if you started out with like I don't know 25, take 117 divided by 25. See what you get. Take 117 divided by 16. Take 117 divided by 9. You just go through your list. You know, I didn't fill them all in because there's an infinite amount. But find the biggest one that divides evenly into the number. Now, just because I'm cheating a little bit here, I have the answers. So I know that 9 and 13. I know the square, like 9 times 13 gives me 117. Now the reason this works, I like to go this route is because, look right here, we know what the square root of 9 is. Square root of 9 is 3. Times, okay, now the square root of 13, alright, so square root of 13 is square root of 13. There's nothing I can do with that because it's a prime number there. So here's how I know that I've simplified these all the way. This radical cannot be broken down any further. So I just make sure I just write it like this. And this is what's called simplest radical form. Let's jump over here to look at this one. All right, so now I have something already sitting outside here. This 2 is fine. I'm not worried about it. It's just kind of there. We're happy. Now, I have the cube root of 48. Okay, so now I'm having to think not perfect squares, I'm having to think perfect cubes. I followed the same process as I did back on the other one, except I'm taking the perfect cubes and I'm going to divide each one of them into 48, and I'm looking for the biggest one in the perfect cubes that divides into 48 evenly. So, because again, kind of cheat because I have the answers here. I know that the cube root of 8 times the cube root of 6. 6 times 8 is 48. Now, the reason I chose that is this. I know what the cube root of 8 is. It's 2. So 2 times, and I bring this 2 down. Now I ask myself, okay, cube root of 6. Can I break the cube root of 6? Let's see. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. So there's nothing that's the perfect cube. 6 is not a perfect cube. There's nothing that'll go into it. So I know that I'm finished here. So I'd say, okay, cube root of 6. Alright, so 2 times 2 here is 4. You get the cube root of 6. And it's done. Alright, let's take a look at this third one here. So I got the square root of 32 x to the 4th y to the 9th. So let's break this apart. Let's say, alright, I like to say the square root of 32 times the square root of x to the 4th times the square root of y to the 9th. So 32, let's see, 32, so I know 16 and 2. So square root of 16 times the square root of 2. Now, this might be slightly new of a concept, so let me show it to you this way. Here's how when I first teach this, I like to, explain it just to kind of get the concept across. So, x to the fourth is like saying this, right? There's understood a 2 out here. I can circle pairs of x's. Okay? That's kind of like saying this. Would you agree? And the squared and the squared cancels each other out. And that's like saying x. So this x squared becomes x. The square right here cancels and x. So I have x squared. Let's take a look at, and you'll see it a little bit better with this one. So y to the ninth is like saying y squared times y squared times y squared times y squared. I'm right out of room there. Let me show that up. Let me show that up here. That's like saying this. 2, 4, 6, 8, and 9. So there's still a 2 out here, right? So I have 1, 2, 3, 4. There are going to be 4 y squareds sitting outside. So that's going to be a y to the fourth radical y. Here's why I know this works. Back when we was first learning logarithms, if you'll remember, there's a part in the lesson where I showed you, and I'm going to come up here. I showed you this right here. Hang on, let me write it down. I'll get my hand out of the way. Where it was power over root. That was the root. I call that the power. So think about what I'm saying right here. Let's just take one of these just as an example. So let's say I just did this. That's the power, that's the root, right? You're saying y to the 2 over 2. Well, what's 2 over 2? It's 1, right? That's why I'm saying square root of y squared is 1y. That's going to be 1y. That's going to be 1y. That's going to be 1y. So I have y to the fourth outside, radical, and then that 1y that never made it out. By the way, this 4 is not the index number. I wrote that kind of close. So let's write all this kind of. Let's finalize it. These are pretty extreme. So let's see. Squared y to the fourth radical y. Square root of 16 is 4. Let's see. X squared goes outside too. The y to the fourth goes outside. And the only things I have left under radicals is the 2 and the y. And that is done. And I have no doubt that everybody's probably scratching their head right now and going, oh God, of all times that baby could be born, if he's not here, this is what he would teach. Relax. I'm going to do 1 or 2 more with you to kind of get the point across. So, don't freak out. Let's see. Let's do it. Let's do another one here. I gotta move around a little bit. Let's see. I'll tell you what. Let's do one that's just has nothing but letters in it. Let's not go overboard with it. Let's kind of keep this nice and neat. So let's take a look at this. If we apply what I was showing you just a second ago, this might help. So here's power. Here's root. Power. So let's take this a step at a time. So I'm looking at the fourth root of w to the fourth times the fourth root of v 16. Okay, let's convert this over. Power root 4 over 4. Power root 16, 4. That's 1W. 16 divided by 4 is 4. So your final answer is WV 2 the 4th. And it works out just nicely like that. So let's do a couple more. Let's do a tricky one. 4th root 48 m to the 8th m to the 3rd. Again, break it apart. All right, so I take it a piece at a time. So I need to think perfect fourths, and here's where you just have to just get in there and just make your list. So let's see, 2 to the 4th, 16. 3 to the 4th is 81. Da 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 da. And you fill that list in from there. Y'all gonna handle something like that. So let's tackle this one first. 48. I happen to know that 16 and 3 is 48. So I can take that and I say, all right, I'm sorry, 4th root of 16 times the 4th root of 3. 4th root of 16 is a 2 times the 4th root of 3. Let's take this, power over root, m to the 8 over 4, which is m squared. Then this one, power over root, n to the 3/4. Now, if you notice right here, this doesn't even, 3/4 doesn't even break down any. So really, at this point in our lesson, let's not worry about leaving it in this form. Let's just leave it like it is right here. If you're very astute, you have probably noticed that when this number is less than this number, it doesn't clear. If this number is bigger than this number, then it does clear the radical. So there's a little handy dandy trick to kind of just gauge if something's going to break down or not with these. So everything's outside the radical, we group up. We got 2m squared times, and then you get your 4th root of 3n to the 3rd. Let me make sure I'm not missing anything. Nope, yeah, got it all. So there's your crash course in simplifying radicals when they're bigger than just a basic square root. So if you like this video, hit that subscribe button.